Morning. Okay, good morning. Assalamualaikum everyone. Last class, okay, before our midterm, last week we had done chapter 3, the first law analysis. Today we will proceed with chapter 4, which is adiabatic flame temperature. We will have for chapter 4, we will have adiabatic flame, then combustion with water gas equilibrium, process monitoring, then only we will go for the combustion appliances. Okay. Okay, for chapter 4, adiabatic flame temperature. From the term adiabatic itself, what do you understand? What is adiabatic? No heat transfer. Q equals to 0. Okay, so the enthalpy, the heat calculation previously, where we should calculate the Q equals to product minus reactant, right? So for this adiabatic, it will be product equals to reactant. Okay, last time we had H product minus H reactant. So in adiabatic, where Q equals to 0, so you will see products equals reactant. Okay, so in this chapter, you will need to predict what is the flame, the adiabatic flame temperature. Okay, there are two cases where we have constant pressure and constant volume. Okay, P constant, P volume. Constant P, constant V square. Okay, the adiabatic flame temperature, it should be the highest temperature that can be achieved in combustion system, and where Q equals to 0, and it depends to the air-fuel ratio. It depends to the air-fuel ratio. Maximum flame temperature for a given fuel occurs at a stoichiometric air-fuel ratio, but it will be even higher when it uses pure oxygen. Okay, when no nitrogen involved, only oxygen, the flame temperature will be higher. Okay, then the two adiabatic flame temperature, you will have two cases, constant pressure and constant volume. Okay, we will see later on the two cases, and the equation might be a bit different for the two cases. Okay, this one is for constant pressure. As I mentioned earlier, for constant pressure where Q equals to 0, so total heat in the reactant is equivalent for the product. Okay, in equals to out. At T adiabatic. Okay, remember last time when we calculate the sensible heat, when we calculate the heat for a particular component, you will have heat of formation plus sensible heat. Sensible heat is at specific temperature minus heat at reference, enthalpy at reference. Remember? So this one last time it is given at specific temperature. Let's say product released at T 1000 Kelvin. So you should find the inputs at 1000 Kelvin. But now for adiabatic, this T, the enthalpy at T adiabatic. So the T over here is T adiabatic, where Q equals to 0. The temperature when Q equals to 0. So this temperature is the one that you need to find later on. This is the unknown. Okay. Now we go for one example, constant pressure. Consider a combustion of liquid octane with HF, this one, from A26, table A26. So in the open system with 50% excess air. Calculate the adiabatic flame temperature. Okay, T adiabatic. Assuming that the combustion is complete and reactant enters at 25 degrees C. Okay, you have your fuel, which is liquid octane, and air. Air is the O2 plus 3.76 N2. Okay, and this is your product gases, complete. Okay, complete, and you have excess air. So what are in your product stream? CO2, CO2, H2O, O2, N2. Okay, this is excess air. So you will have O2 in your product. The reactant enters at 25 degrees C. So T inlet is 25 degrees C. It asks you to find out T adiabatic. So T adiabatic is the outlet T. Adiabatic, so Q equals to 0. Okay, first thing first, always generate the combustion equation. Okay, in your calculation, you must show this combustion equation. It will contribute some marks to this. Okay, so this is your fuel, liquid octane. This is the actual A. Okay, A actual. How to get this A actual? How to get A actual? Formula. A strike. Right. 1.5, the excess air. Excess air is 50%, so theoretical air is 1.5. Multiply by A strike. A strike is the one you calculate from the formula. The AX plus Y over 4. Okay, so this 18.75 is the A actual. Okay, do the balance, you will get this figure. The mole produced, the mole of gases produced. Okay, now from there, you are required to calculate the T adiabatic. So to calculate the T adiabatic, we need to use the first law analysis, first law equation, where enthalpy of the reactant equivalent to enthalpy of the product. Reactant fuel plus O2 plus N2. Okay, and product CO2, H2O, O2, and N2. Okay, you will need this info, the HF for each component, and also the heat enthalpy at reference. Okay. Calculate Q at two different temperatures. Then do the linear interpolation or extrapolation. Okay, to get temperature at which Q0. Yeah, follow me step by step. Here, for the solution, it assumes the temperature is at 900 and 1500. Okay, you must assume two temperatures. How to assume? Simply assume. Okay, we'll see. Okay, this one, T900 and T1500. Now you find out the infos, all the infos at T900. We have the component, we have the fuel, C8H18, O2, N2, CO2, H2O. Okay, so find out what is the HF for each component, then find out the H at 900. Then find out the H at reference, 298 Kelvin. Okay, then find out the heat at 1500. Okay, the value over here will be different because this value they are using different properties table. Now using the thermodynamic properties table, find out all these infos first. Find out all the infos. Heat of formation for each component, enthalpy at 900, 298, and 1500. Enthalpy heat of formation for liquid octane been given in the statement over here, 249950. Okay, find the rest. Using the thermodynamic properties table. Heat of formation, we refer A26. Okay, liquid octane. Uh, 249950. Get bigger. Okay, O2 and N2, 0. Sorry? Equation. This equation. Huh? Water, liquid, or vapor? You can put your own assumption. In this calculation, okay, from the statement over here, it doesn't mention liquid, the H2O is vapor or liquid. Okay, you can give your own assumption. This answer, okay, this answer, the final answer over here is based on water vapor. I assume the water is in vapor form. Okay, HF for CO2 393520. H2O assume vapor. Okay, once you determine all the heat of formation, find out the enthalpy at 900 for each component. Octane, there will be no info because it is not released. Okay, for water, this is the figure. Enthalpy at 900. Water, water 31828. Then find for 1298 as well, that reference. This is the figure. Okay, then also find for 1500 for each component because we assume two temperature. Okay, how to simply assume the temperature? I would suggest you to assume in between 1000 to 2000 temperature. Usually, the answer will be in between that range. Okay, so find for the rest. Okay, you should be getting this figure for the product gases. Okay, once you gather all the info, plug it into the equation to find the enthalpy at T900 and T1500. HF for octane in your slide. This one is the correct HF. Please correct it in your slide. In your slide, it's not from thermodynamic properties table. It's from other table. Okay, so this is the correct value for HF of octane from table A26. Okay, so don't get confused with the solution over here. This one is from the original value. Okay, this one is HF for octane in the previous slide. Okay, this one we should correct it. Okay, that's why I highlight over here. This one is not the figure that you will get, because these all value over here are using different table. This value is the one that you should be getting. 300 something. Okay, so you should be getting this figure for T at 900 and T 1500. You get the same or not? Different or slightly different? 900, what you get? Okay, how about this one? What you get? 1 million? 118 6728. 0.5. This figure value all same.
Yes.
You get the same. I think for 900 one. For which one? For which temperature? You get 3. 350, okay. 1500.
The operation of
Heat of formation for 393. 393, right? 393. So it's 393. Okay, so if you get the figure from the table correct, then your calculation should be correct lah. So the step is correct. Once you get the enthalpy at T900, then find out enthalpy at T1500. Okay. So once you get the figure over here, do the interpolation or extrapolation. Depends to the case. Okay, so I suggest you to put in table to see it clearly. For 900, this is the figure. Okay, for 900, I'm using my calculation. If you get slightly different, then you just use your calculation. Okay, so from here, list down all the infos that you already calculated. Then Q at T adiabatic, which is the unknown T, should be 0. Okay, so now our unknown is T adiabatic. Okay, now calculate the T adiabatic. Do for interpolation. Okay, input all the known figures, and from here you'll get your T adiabatic is around this figure, 1774. For the enthalpy at both temperature, if you get slightly different, then it's slightly different is okay, acceptable, as long as it is in the range. Okay, and the T adiabatic as well, as long as it is in the range. Okay, this T adiabatic is depending to the temperature that you choose. This one is based on 900 and 1500. If you choose other temperature, you will get different T adiabatic, slightly different. Okay. Okay, later you check your calculation. I need to proceed. Okay, we proceed with this question. Another example. This one from textbook. It asks you to calculate the T adiabatic of methane when it is burned with 30% of excess air. Okay, you will have a methane as a fuel and air. 30% excess air. So your product stream will have oxygen. Adiabatic flame temperature. So T adiabatic when Q equals to 0. This question, it doesn't give you the inlet temperature. So we can assume at room temperature, which is 25 degrees C. If it doesn't give you any infos for the inlet temperature, you can assume on your own. The data that you will be extracted later on will be based on the temperature that you assume. Okay. So this one, I assume T inlet to be 25 degrees C. Now, first thing first, generate the combustion equation. Okay, what is your A over here? A actual. Two, 2.6. 30% excess air, so theoretical is 1.3. Multiply by 2. Okay, 2 is from the A start. Okay, so your CO2, how many mole of CO2? 1, correct? H2O, 2, O2, do the balance to find out. Okay, then the N2 here will be 3.76 multiplied by 2.6. Okay, once you generate the combustion equation, next step is find the data. Find the data for each component. Okay, generate the table. The HF Okay, here you need to assume two temperature for the tea adiabatic. Okay, so it depends to what temperature that you assume. Find the enthalpy at that particular temperature, HT1 and HT2, and also the enthalpy at 298, the reference. Once you get all the data, step 3 is to find out the T adiabatic, where Q equals to 0, H product minus H reactant. Then at the T1 and T2 that you assume, you will get their own and heat value. From there, do the interpolation. Okay, step 4, interpolation. Okay, I'll give you the range of T adiabatic that you will be getting. If you assume if you assume T1 is 1000 and 2000, I make it larger. Okay, these are the range of the T adiabatic based on the T that you assume. So basically the range is from 1900 to 2000, the T adiabatic. It depends to the range of your temperature. Okay, any question? Make sure you know the steps. Actually, this is the simpler way to calculate P adiabatic. If you check the textbook, it has another options to calculate the P adiabatic where we use to assume based on enthalpy value. That one is a longer step, longer calculation step. This is a simpler step. Okay, that one I don't plan to. Perhaps I can introduce you in the next class on how to calculate based on the enthalpy basis. Okay. Okay, so next class, we will go to that. I will introduce you on that enthalpy calculation assumption, and we will go for constant volume, which the equation will be slightly different. Okay. Okay, make sure you understand the step for constant pressure first. Okay, any question before we end the session? Again, I repeat for the T adiabatic, it depends to the two temperature that you assume. Okay. As long as it is in the range, it is acceptable. Okay, that's all. Thank you.